or dynamometer. We spend a lot of time on light duty. Basically, every vehicle that's sold in the US has to be certified through EPA. And so our lab does a lot of audit and confirmatory testing as part of that program. We also do some benchmarking, future technology analysis. That sort of leads into modeling and policy evaluation, all really to develop and implement regulations for the transportation industry. So just a couple other things there at the bottom. We also do voluntary partnerships, things like SmartWay for heavy duty freight, consumer information, so the vehicle labels and all the information there that you'd see when you go buy a new car, as well as certifying and regulating fuels and working on the renewable fuel standard programs and things. So that's just very quickly kind of what we do. Today I was really going to kind of talk mostly about advanced technology, so connected and automated technologies, kind of in the context of our regulatory rules. So just real quick, there are rules now in the books on place through model year 2026. So that's the existing rules. That's kind of what I'm probably going to be talking mostly about today. But I want to kind of tee up two questions before I get too far into this. And the first is, how do we deal with advanced technologies under the existing regulations? And that's, like I said, that's mostly what I'm going to talk about, and hopefully I'll more or less answer that question today. But also, how do we think about these technologies beyond 2026? In the automotive world, model year 2026 is not all that far away, really. And I think this is something we're certainly thinking about at the EPA. I know many of you are as well. And certainly I think the conversation that we want to have with many of you is, not just how do we fit some of these technologies into the existing regulations, which is, as Anna kind of alluded to, is difficult, but also how do we think about building a better regulation that, beyond 2026 that can better account for some of the new technologies, the new business models that are really kind of taking place in this industry. So just keep that in the back of your mind while I'm talking about the existing regulations. So I know many of you know our programs well, but just quickly, this is actually an average or a credit-based program. So it's an averaging banking and trading program, is what we call it. So at the end of each model year, the way that we determine compliance for each manufacturer is basically, do you have credits in the bank? And manufacturers can trade credits. They can generate credits if they have a good year where they're below the standards. They can create a deficit and offset it with credits if they have a year where they are above the standards. And you can also carry actually a deficit forward for up to 3 years. So it gives some flexibilities to manufacturers in how they can meet the standards. Part of this, sort of the building blocks are within each model year, we calculate the model year standards, and that's based on the vehicles that each manufacturer sells. Then we also measure what we call basically their performance. And so that's their tailpipe emissions. And then there's some various what we call flexibilities here, which is a couple of things. It's related to air conditioning credits, EV incentives, electric vehicle incentives, and also off-cycle credits. So that all kind of goes into the model year calculation. I don't want to go into too much detail on this, but I will say this is all from many of the graphs I'll show here from the EPA Automotive Trends Report. There's far more information there, and I'll point you to that if you have detailed information, or I'm happy to answer questions later. But mostly I'm going to kind of talk about these sort of flexibilities and off-cycle credits today. So what are off-cycle credits? So the regulatory program that we have is largely based on two tests, a city test and a highway test. And those tests are really, have been part of CAFE since 1975, and they're actually written into the legislation for CAFE. So when EPA started doing greenhouse gas standards, we adopted using that same approach so that we could harmonize with CAFE standards. And those two tests are really good for a long-term, consistent baseline of testing. But I think we all know technology and driving habits and things have changed. They do not capture everything. They do not capture the world of technology out there. And so one of the remedies that was created in the existing rules was this idea of off-cycle credits. And it is exactly what it sounds. It is credits for technologies that have emissions or efficiency impacts that are not captured on the test themselves. And so like we said here, this is just sort of some of the Code of Federal Register language, but we're really looking for measurable and demonstrable kind of technologies that have an impact on greenhouse gas emissions or efficiency. And then three things here to be aware of is things that are explicitly excluded from being eligible for off-cycle credits are things that are integral to basic vehicle design, required by some other federal law, or attributable to crash avoidance systems. So how do you generate off-cycle credits? There's 3 ways to do that. The first is we have an actual menu of technologies, and I have a couple listed here. And this is basically just a checklist. I mean, manufacturers have to tell us they produced X number of vehicles with start-stop technologies on their engines, and they get a set number of credit for each of those vehicles, more or less. The math is a little more complicated, but that's effectively what it is. They basically tell us they have these technologies and they claim a credit, and it's pretty straightforward. They're fairly conservative credits that we set up intentionally, partly because this is an easy program and there's not a lot of independent testing going on behind this. And not surprisingly, most of the credits that have been awarded under the off-cycle program are these menu-based programs or credits. The second way to do this is 5-cycle testing. So in addition to the 2 cycles, we have 3 other tests that we use, a high-speed test and basically a cold start and a hot test. And those 5 tests are what we call 5-cycle, and that's what we use for labeling. So when you see a vehicle label on a new car, that's based on the idea of 5-cycle testing. So you can do A to B testing and basically prove that your widget improves fuel economy, X amount between A and B testing. And almost no one has done that. And it's also not really relevant for connected and automated vehicles. I'm not sure you'd be able to do that. And I should say connected and automated technologies are not on the menu currently either. So when you're talking about connected and automated type vehicles, there's really only this last option available. And that is basically prove it to us. And that's really pretty much the extent of what that is. And some people have done that. We have certainly awarded credits through that. But that's basically the only way that I think we could approach connected and automated vehicles under the existing rules. Just for a little bit more information about the menu credits, this is just an interesting graph that we put together this year, or last year, looking at manufacturers and what menu credits they're claiming. So again, you see sort of a little bit more detailed list of what's available down at the bottom and then how manufacturers are using it. So you can see almost everybody is using off-cycle credits to some degree, at least the menu credits. Although, with varying different amounts for what technology they're using and what's appropriate for the vehicles that they make. So back to this alternative methodology for creating off-cycle credits. Basically, this is sort of the criteria for getting that process started. And EPA is looking for, modeling, on-road testing, on-road data collection, or some other approved analytical engineering methods. It must be robust, verifiable, and capable of demonstrating real-world emissions. You have to have a baseline and a control to kind of evaluate that difference. And so basically, we're looking for a lot of data. We're willing to say, prove it to us, and you can say how, but this is a fairly heavy lift on what's acceptable and how you can do that. And you need to come, applications need to be quantified and verified, and that's difficult to do with a technology that's kind of possibly out sort of in the future too. So this is not an easy process. People have absolutely done it, but I don't want to imply that this is easy to do. This last bullet, EPA must seek public comment and publish each application. So when manufacturers bring us an application, we are required to publish that to the public and take a comment period. And I forgot to look at what exactly that comment period is, but that's automatically probably at least 30 to 60 days where that's open just for people to review it and comment it outside of the agency. I do have one example here that I'll walk through, and this is actually an older example, but I still think one of the more interesting ones. Mercedes came to EPA and said, we know start-stop is on the menu, but based on our vehicles and the way people drive our vehicles, we don't think that's enough credit. So we're applying for more credits for our off-cycle technology. They came to that, we published that, we got 8 public comments from a couple auto manufacturers as well as NGOs. And so we went through a process with Mercedes. I think we kind of went back and said, show us some more. They instrumented, I believe, 29 vehicles, and then also went out to Progressive and bought some of their data that they'd used, that they had gathered using some of the dongles that I think they had allowed people to do through their insurance programs. But again, they got data on 1.4 million vehicles. EPA looked at that data, Mercedes looked at that data, cut it in various ways, looked at how start-stop was being used in the real world, how Mercedes drivers and vehicles were using start-stop in the real world. It had a process where we went through to eventually EPA did approve a little bit more credits, but it was a conservative approach still. And as you can imagine, again, this is not a simple process. This takes a while, but it is an option, and it's certainly available to people to do this. So a little bit more, just no manufacturers have requested credits for automated or connected vehicles at this point. I haven't checked in the last month or two, but as far as I know, no one has. And I'm a little surprised by that. I would have thought we would have seen something for adaptive cruise control or something, but we have not. Most requests were related to the technology on the menu, so either more credits or retroactive credits. And many of the credits that we have applied for other things are related to these two technologies. So air conditioning compressor and a high efficiency alternator. And these are interesting too, because these have been now applied for by more than one manufacturer. So for the high efficiency alternator, someone came through and we approved it. I believe it was a Denso component. And so other manufacturers said, well, hey, we're using that too. And so that also then kind of went through that process and was approved. And so interestingly now with the SAFE rule, which I'll touch on in a minute, that technology has actually moved into the menu. So we have now added technologies to the list of what can be considered part of that menu. And all of these are available online. I put the website here. If anyone wants to go look at this, please do. The Mercedes one is about 20 pages, I want to say, and it's actually, compared to some of our regulatory stuff, it's actually pretty readable. So, if you're interested, please feel free to go look at that. Just to put that in context a little bit, in 2018, which is the last year we have sort of final official compliance data for, that performance value is across the industry is 253 grams per mile, and that included about 6.5 grams of off-cycle credit. You can see here again in the graph, almost entirely, or a large portion of that was these menu credits, but a few non-menu credits. And some manufacturers are up in the 10 plus gram per mile range, which is very significant to them. Again, this is just, looking back a little bit. The dark blue boxes here are the standards for each manufacturer. We actually do a car and truck standard, not an overall standard, but we put this together for illustrative purposes. And so that's their standards. The lighter blue bars are what manufacturers actually achieved each year, or in 2018, as their performance value, including off-cycle credits. So you can see 6-10 grams per mile. Again, it makes a big difference for some of these manufacturers. And I always have to say, this is not how we actually do compliance. This is just a snapshot of how manufacturers did in 2018. And it's not relevant to this one, but people are going to ask. So Tesla, the reason Tesla is so negative in this one is due to the EV multiplier. For each EV that was sold in 2018, it gets to count as 2 vehicles in the regulatory world. So instead of being 0 to 228, they get more of a 400 gram per mile credit essentially for each vehicle they sold, which is a lot. So again, just for context, I will include this. This is actually more how we look at compliance and do manufacturers have a positive credit balance at the end of the year? So you can see almost every manufacturer of Jaguar Land Rover is the only one that didn't in 2018. And this list is interesting because it's not really the same order of who did well and who did not in 2018, because credits are traded and purchased. And move between years as well. And we do know there's an active credit market. Manufacturers are selling and buying credits, and it's a valuable market. So just quickly, impacts of the SAFE rule. Obviously, the SAFE rule was the updating of the greenhouse gas rules that came into play earlier this year. It expands the program one model year from 2025 to 2026, significantly lowers the standards in the 2021 to 2026 timeframe. For this conversation, like I already touched on the high efficiency alternator. So one interesting thing is moving technology to that menu. That's something we hadn't done before, and it's something manufacturers have asked for. So that is, clearly something that we're considering is what technologies should be on that menu. And if, I think if we've have technologies we have a comfortable number for, that's kind of the pathway that they would, if we're to continue this program in the future. The second thing that's important that a lot of people ask about is suppliers. And late in the process, there was a commitment that EPA will create a process to begin allowing technology suppliers to begin the petition process for off-cycle credits. And that's new. It had always only been with OEMs. I wish I could tell you more, but I don't know more. And I think this is about the only statement in the rules, so we will have to see how that actually develops. But that is something that is new. So looking forward, again, I kind of tried to list those two questions at the beginning of the presentation. So first of all, again, the existing regulations out to 2026, can connected and automated technologies create credits under the existing regulations? And certainly in theory, the answer is absolutely. There is a pathway to do it. It would require basically this petitioning of EPA for off-cycle credits. And it will require data. It will require some modeling, some instrumentation. I don't know exactly what, and the regulations don't specify what that has to be. But you have to bring EPA enough data to convince us, and this is not me, this is another team, but to convince EPA that this is something real, that this is a real benefit to the environment, to efficiency, outside of what the rules capture, and that it's something that's verifiable and repeatable, across the spectrum of how vehicles are used. So it's not easy. We are telling people, please, if you have interest in, you should be collecting data. You should be anyway, if we can want to talk about this. So like I said, off-cycle applications are data and time intensive, but they are an option. So then again, sort of back to the second question that I was kind of posing. I mean, is there a better way, especially looking beyond 2026? How do we think about this in better ways? So how can we help to push technologies that actually do have, environmental and efficiency benefits, kind of without some of the burden, but also, how do we start looking at this in more of a system view? I mean, the way I sort of explain it is EPA, we're very good at drawing our box around a car. We know how to test the heck out of that car on a dynamometer. I mean, we know the emissions testing, and that's how our regulations have been written for 40 plus years. And when you start talking about connected vehicles that interact with their surroundings and other vehicles and infrastructure, and automated vehicles, which could severely change, vehicle miles traveled, or how people how people get around. These are real challenges to how we've written rules in the past, and so I think these are all very much things that we are interested in and trying to think about now. And I think that's a conversation that we look forward to going forward. And I think that Chris will have some really interesting thoughts on things that they've learned from the NEXTCAR program, which is really interesting. I know I was disappointed that I was looking forward to the May test plan out at ACM, but that's too bad that didn't happen. So I think that's enough from me. I'd like to save time for questions. So Anna.
So that's great. Thank you, Aaron. And we have 2 minutes. So actually, I would take the 2 questions that they were posed, if that's okay, Aaron.
Absolutely.
There are 2 technical questions. One from Kate Whitefoot from Carnegie Mellon. By the way, perhaps I missed, I said that Aaron is my neighbor, but he's actually a graduate from Carnegie Mellon and University of Michigan. So there we have a professor now asking a question. It's saying, what was that?
And Anna,
yeah, go ahead.
Yeah, thank you. Aaron, I do have one technical data question in the chat if you just want to check it later. That would be great, but maybe more meaningfully. Can you talk about the restrictions and flexibilities that EPA has in the timing of adjusting any of the credits? So let's say you gave one example where with a petition, the credit was increased. Getting the credits right for CAVs is going to be difficult. As more data comes in, do you have the flexibility to adjust those up and down, and what sort of restrictions are placed on EPA in adjusting them?
Yeah, so currently I don't know that we have that explicit flexibility to kind of adjust things. I think the way it's written, it's the off-cycle credits were really written with the intent more of, we have technology widget X, if it's on the car, if it's off the car, what is the difference? I think that's more of the thought process and how that was defined, and that doesn't necessarily fit well to kind of, technologies that need to be out and gather data in real time. We have allowed people to come back to us and sort of retroactively apply for credits in previous model years. So people have certainly been applying for credits in the past, not necessarily changing credits, but applying for credits that they didn't tell us that they had or didn't apply for at the time. Although my understanding is we have very much now tried to shut the door on that, partly because the whole off-cycle credit, especially sort of that third pathway, is very time intensive for us just to evaluate. So yes, I think that's basically the answer is that we don't really have that flexibility. We have talked about it. I mean, if we're looking forward, do we need to somehow be able to apply a tentative credit that will allow someone to have for technology, but then come back and adjust it based on real world data or something? I think we're interested in that. I'm not quite sure how we would do it, but it's certainly a topic that I think is interesting.
Great, thanks, Aaron. I think there's a question also from a statement, I would say. No, there is also a question there from Greg Keolian regarding the boundaries. I think you touched upon as he was typing. Maybe we can take the answer for that after the Chris's presentation and at the broader discussion and Q&A. So with that, I would like to actually now start on time, 2 minutes late, with Chris Atkinson. Chris, you are on if you want to share your slides, because he can tell us what is possible. And I think, I hate to say, it's kind of like Aaron told us how difficult it is to understand the possibilities.
Thanks, Anna. Sharing slides. Sorry, apologies. Are you able to see my slides? Yeah. Thanks. Thanks very much, everybody.
Yes, thank you.
So good afternoon, I'm Chris Atkinson. I'm going to talk to you about ARPA-E's NEXTCAR program. NEXTCAR was the next generation energy technologies for connected and automated on-road vehicles. As you know, ARPA-E is a sub-agency of the US Department of Energy. Oops. That wasn't supposed to happen. Sorry, I'm not sure what's going on. Apologies. Okay, try again. Nope, there's something very odd happening.
Dr. Atkinson, if I
Your
may.
last slide is selected?
Yes, you just have to scroll up to the to the first slide of your presentation.
Scroll up to the first slide of the presentation.
Once you exit the slideshow mode, on the left, you're on slide 38.
I see. I see. Oh, apologies. Okay. Thank you very much. Yeah, there you go. User error. I had the same slide at the beginning and the end, and I've managed to confuse myself terribly. Sorry about that. Good afternoon, everyone. I'm Chris Atkinson, until very recently, ARPA-E Program Director for NEXTCAR. ARPA-E, as you know, is the Advanced Research Projects Agency Energy of the US Department of Energy. And just firstly, I want to acknowledge our team, because it really is a team. I, as I say, was the program director for NEXTCAR until the 1st of June, in other words, 10 days ago. Marina Sofos has taken over as program director. Mary Yamada is the tech to market advisor. Rusty Hefner, who some of you might know, is a technical advisor on the project too. ARPA-E, as I say, is a sub-agency of the US Department of Energy with the mission to overcome long-term and high-risk technological barriers in the development of energy technologies. And I'll put it in reference to transportation and specifically advanced mobility in a short while. But ARPA-E was created 10 years ago to do three things: to reduce energy imports, which, as you know, are predominantly petroleum, and petroleum is predominantly used in transportation; to improve the energy efficiency of the full energy spectrum, and that's everything from energy generation, storage, transmission, distribution, and end usage; and to reduce the emissions around that energy spectrum that I just described. So why is NEXTCAR, which is a program to improve the energy efficiency of future vehicles, why is it important to ARPA-E? Well, the Sankey diagram, which I'm sure you've seen many times before, and this is the Sankey diagram for 2019, just brings that into context. Transportation, as you know, is the least efficient, outside of energy generation, transportation is the least efficient portion of our energy spectrum. A very small portion of the total energy that we put into transportation is realized in what Lawrence Berkeley here calls energy services, or actually useful energy. And the vast majority of it is rejected. It has about a 21% net efficiency in terms of, in this case, mostly chemical energy in versus useful work output. This shows the same thing. Transportation utilizes 28% of primary energy used in the United States. And of that 28%, it's predominantly gasoline, which, as you know, is used mainly for light duty. There's, of course, distillates, middle distillates, diesel fuel, jet fuel, marine, rail propulsion, so on and so forth, aviation. Again, why is transportation important? Well, since 1950, which admittedly is a very long time ago, while population in the United States has doubled, VMT is up by a factor of 3.5. This is clearly concerning. As you know, VMT is very, very closely linked to economic activity, and it's seen significant decreases since the COVID-19 pandemic started. But in general, VMT is directly traceable to and attributable to economic activity. The two are inextricably interlinked. I had to include some data from the University of Michigan. Here it shows real-world fuel efficiency of vehicles stagnating over the last several years. Clearly, with stagnating fuel efficiency and ever-increasing VMT, it's deleterious for vehicle energy efficiency. Here is the real-world fuel economy. As you can see, this is EPA data, of course, from 2019. It shows that the real-world fuel economy of the fleet is still increasing, but that's because of fleet turnover. We are seeing increasing numbers of much older, less fuel-efficient vehicles replaced by newer, more fuel efficiency vehicles. But again, because of the stagnation in the fuel efficiency numbers for the new vehicle sales, we will see this stagnate as well. And that's clearly of critical importance to an energy agency. How do we make future vehicles more energy efficient? We know how to do this. Downsize, downweight, improve the efficiency of engines, increase hybridization, increase electrification, and then ultimately full electrification. But what about the things that we can't see on this particular roadmap, if you like? What about the effects of vehicle connectivity and automation on future vehicle energy efficiency? And we're considering only vehicle-related technologies and not the interaction of those vehicles necessarily with infrastructure. We're not considering regulation, and we're not considering policy. In other words, on a vehicle-related technology basis, what is there that we can do to vehicles using vehicle connectivity, which is an emerging technology, as you know, and using vehicle automation, specifically at the low levels of automation? What can we do? How can we harness those to improve future vehicle energy efficiency? That was the question that we posed at ARPA-E. Of course, for connectivity, we're talking about both vehicle to vehicle, vehicle to cloud, vehicle to infrastructure, cellular, Wi-Fi, satellite, as well as, of course, machine vision. Again, bear in mind, this is at the low ends of automation, the low ends of the SAE, L0 through L5. In other words, L1, L2, L3 is what we're interested in for the first phase of NEXTCAR, at least. This is just a slide, which I'm sure you've seen many times before, just showing that ADAS, Advanced Driver Assistance Systems, which are at the L1, L2 level, if you like, are ubiquitous on new vehicles. In terms of L1, L2, L3 sorts of vehicle driving tasks, you can think of things like adaptive cruise control, traffic jam assistance, lane keeping assistance, dynamic driving assistance. Again, many of these technologies are available today. So again, the motivation behind NEXTCAR was using those low levels of vehicle automation and connectivity to improve vehicle energy efficiency by 20%. And we considered ego vehicles. In other words, a single vehicle. The single vehicle would obviously interact with traffic around it. It would interact to a certain extent with infrastructure. It would be subject to varying duty cycles, varying operating cycles, varying environmental conditions, if you like. How can you use information obtained through connectivity and the lower levels of vehicle automation to improve vehicle energy efficiency by that 20% number? We produced this cartoon in 2016 or so. It was in our funding opportunity announcement. I do like it because it's still perfectly valid today. It shows the fact that you have a human driver as well as an automated vehicle controller. Can I point it? Laser pointer. A human driver as well as an automated vehicle controller through some sort of conventional vehicle controller interacting with the powertrain controller, controlling the powertrain and hence the vehicle. Significant feedback, of course, from the vehicle as well as from short-range machine vision, V2V, V2I, cellular, Wi-Fi, route information, weather information, traffic information, and so on and so forth. So we initiated NEXTCAR in 2017. It was a $35 million of federal funding and about an extra $10 million in cost share program. And the idea is that there is a significant potential energy emissions reduction in the United States. We consumed last year, as Lawrence Livermore stated in the Sankey diagram, 100.2 quadrillion BTUs per year. It's a silly unit, I know, but it's the unit that the DOE uses. And we could reduce that by about 4.2%, which is a substantial reduction, if we improve the energy efficiency of all vehicles, light duty, medium duty, and heavy duty, by 20%, 20%. We initiated the program, as I say, in 2017, 11 projects in the universities and companies that you see here, 7 light duty, 2 medium duty, 2 heavy duty, 4 fuels, gasoline, natural gas, diesel, and electricity, and a range of vehicles, a range of vehicle vocations, a range of different technologies. Now, of course, as you know, any new automotive technology there's certain requirements that it needs to meet in order to replace an incumbent vehicle technology. The new technology has to be comparable to or better than the incumbent technology in these 8 areas. And they are performance, and there's various measures of performance, but you can think of things like power density or perhaps energy density if you include the energy storage capacity. And this is normally a requirement due to customer acceptance. There, as you know, in FMVSS, there are various safety requirements around minimum vehicle acceleration rates and things like that. But typically, most vehicles are well beyond that. And so performance tends to be a customer acceptance requirement. Efficiency, fuel economy or energy efficiency, as you know, is subject to regulation through both EPA and NHTSA. Regulated criteria pollutant emissions are regulated by the EPA. The costs, and by that we mean the total cost of ownership, including the ongoing energy cost or fuel cost, is normally a customer acceptance requirement. Reliability, mean time between failures, maintainability, etc. And then there's a catch-all category of utility. How useful is this vehicle to anyone? How useful is this powertrain or propulsion technology to the driver or to the user or to the owner? And there's things like acceleration, drivability, MVH, cold or off cycle operation, ease of use, transparency of use to the end user, the operator, the driver. Fuel acceptability, we included that in NEXTCAR in order to make sure that the fuels that would be used by these vehicles would be ones that would be readily obtainable in the near future. And then, of course, safety is non-negotiable. It's a subject both of regulation, as you know, as I said, through FMVSS, crash testing, but as well as customer acceptance more and more. NEXTCAR has the participation of a number of OEMs, including GM, Toyota, Cummins, Hyundai, and Volvo Trucks, Tier 1 suppliers, and a number of system integrators, connected and automated vehicle service providers, and others. We pride ourselves at ARPA-E in developing these ecosystems. We bring together, we believe, people who ordinarily wouldn't be brought together in order to solve the problems that we set out to people, the problems that we challenge them with. Our 2019 annual review, I sort of include this slide because of, well, the sense that we're missing a lot of this nowadays, now that we're not able to meet in person. Anna spoke about that earlier. Exactly a year ago at our 2019 annual review, we had significant attendance and participation by all the people that you see on this slide. And unfortunately, that's an element that's missing right at the moment, but hopefully we'll get back to it. So what technologies did the NEXTCAR teams develop? It turns out we had no particular set in mind of what technologies people might implement or what technologies they might use. It turns out that they ended up developing fairly similar technologies between the teams. The first being eco-routing. Of course, as you know, Google Maps will route you in the most time-efficient or speed-efficient way from any origin to any destination in the United States or indeed worldwide. But of course, that misses out the concept of the energy associated with the energy expenditure across. As it turns out in the development process, most teams ended up using sort of the chain, the value chain, if you like, from the cartoon at the bottom of the slide. Simulation, modeling, software in the loop, modeling in the loop, hardware in the loop. These things are very well established and used for a long time. We're quite proud of the fact that at NEXTCAR, a number of the teams developed very, very sophisticated dynamometer in the loop testing. What do I mean by that? Well, the vehicle will be driving on the dynamometer, and instead of being driven over a prescribed vehicle velocity versus time trace, the desired velocity of the vehicle would change in real time in response to, for example, inputs from a traffic simulation model, or would change in real time in response to a probe vehicle that was out on the road at the same time and operating in real traffic. Again, people have spoken about this for some time. We're very proud of the fact that a number of teams implemented this and developed it and furthered it significantly during the conduct of the NEXTCAR Phase 1. And then, of course, there's on-road testing in the end. In terms of the timeline, we were due to be completed roughly now in 2020. All 11 teams would have completed their 3-year project at about this time. Of course, the COVID-19, which I'm showing there as a red lightning bolt, has delayed that and has probably delayed it by 6 months or more. So, as I say, I rotated off as the program director responsible for NEXTCAR, and Marina Sofos has come on as the program director who will see out the balance of the NEXTCAR Phase 1 program. We hope to have final demonstrations on track at the end of the project. Exactly when that happens, whether that'll be in calendar year 2020 or calendar year 2021 is yet to be arranged. Now I'm going to show you program level results of a number of the teams to date. Now bear in mind that the NEXTCAR Phase 1 has not been completed, but is approaching an end. And point 1, we give it a name and it's bold-faced. Bear in mind that all of these results are vehicle specific, vehicle duty cycle specific, traffic density specific, technology specific, technology penetration rate specific, in some cases weather specific. And not all these efficiencies are additive, but of course some are. In fact, some are multiplicative, in other words, beyond additive. And we're presenting these results without context. They're simply presented as results. The results between the various teams and the technologies are not directly comparable. See point 1 above. Point 1 is clearly recursive because we refer to point 1 within point 1. But that merely is a double reinforcement that anytime you see results pertaining to connected and automated vehicles, you do need to think very, very carefully about how they derived, where they were derived, what sort of driving behavior was involved, what sort of surrounding traffic was involved. Because each and every time these vehicles are either tested in simulation, as I said, in something like Dyno in the Loop, or in the real world, the results that you achieve will be different. Now, perhaps I should have said that with a small voice because Aaron Hula is on the video conference, but it's something that's unavoidable. In other words, every time you test these vehicles, because they interact with their surroundings and on a continuous basis, the results that you get will be different. Some of the results that you see are simulated, most are experimental. But the experimental includes Dyno in the Loop and on-road. Some are real-world data too. And of course, as Aaron was mentioning earlier, how does one gain credit for these energy efficiency improvements if there is no longer a test cycle per se? And of course, as discussed, off-cycle credits are one possibility. So you can see across the top, Michigan Tech, University, GM, Ohio State, Southwest Research, University of Delaware, University of Michigan, University of California, Berkeley, University of Minnesota, and University of California, Riverside. Again, bear in mind, these are varying vehicles. Not all of them are light duty. There are some medium and heavy duty. Their vocations are different. The vehicle sizes are different. The particular duty cycles over which they were tested and measured are completely different. It just turns out a number of the teams, for example, developed eco-routing strategies quite independently. And you can see the range of usefulness of eco-routing, for example. Eco-approach and departure, eco-driving or eco-cruise, powertrain optimization, that's sort of a catch-all category, which includes, for the hybrids, and the plug-in hybrids, a significant amount of real-time in situ hybrid energy, hybrid power split optimization, and hybrid energy flow optimization. Powertrain optimization, those are more for the conventional powertrains. And then there are some teams who looked at things like thermal system, platooning, intelligent HVAC, cooperative adaptive cruise control and not simply adaptive cruise control. And then in the UC Riverside case, Eco Stop and Launch, that is the only bus application that we had. So I want to draw your attention to a number of things, one of which is that there is some sort of convergence in the technologies that people found most useful in the NEXTCAR applications, but all of these were developed independently. All of these were applied independently. All of these tested independently. And of course, as I say, they are vehicle technology, vehicle duty cycle, vehicle operating condition specific. We're here lumping all of these technologies from these teams together and then assigning an average energy efficiency improvement. Eco Stop and Launch, again, is the bus application, so that's unique to one team. But you can see things like intelligent HVAC, eco routing, eco driving, eco cruise, eco approach and departure, powertrain optimization, cooperative adaptive cruise, compact platooning, thermal system optimization, and predictive cruise control. Again, we were seeking a 20% energy efficiency improvement. And so, as I said, bear in mind, not all of these are additive, not by any means. Some of them are supplementary and complementary. But you can see that it is actually probably feasible through the selective combination of a number of these technologies, in many cases, to achieve that 20% average energy efficiency improvement. And I should have mentioned earlier that that is over an L0 2017 baseline vehicle. That's the energy efficiency improvement. Here we're looking at the commercialization potential. Something I should have said earlier is that ARPA-E is not simply interested in doing the science for the sake of the science or doing the research for the sake of the research. We do require that the technologies that we fund are at least set upon a pathway to commercialization. Here we're showing the same information in two different ways. But eco-routing, for example, we see as having very high, very immediate commercialization potential. And in fact, a number of the OEMs who worked on the NEXTCAR program are in the process of inserting eco-routing into their product development pipelines. Of course, as you know, once it enters that, it's 3 to 6 years or potentially even more in some cases before you see a commercial product emerging on the other side. But we're very happy to know that eco-routing, which has been spoken about for a number of years, but has been implemented in a number of these projects, NEXTCAR projects, is well on its way to commercialization. This is simply showing in a cartoon fashion the real world energy savings potential on the horizontal axis versus the commercial potential for these L1, L2, L3 connected and automated vehicles. I should have shown the slide earlier, but it reinforces the fact that ARPA-E requires that there be some transition towards market adoption of the technologies that we find. So what lessons have we learned? Well, we learned an enormous number. But the most important was that the lower levels of automation, L1, L2, L3, have the potential for significant energy efficiency improvements. And it can deliver beneficial short and medium-term energy reductions for the operations of a range of vehicles, light, medium, and heavy-duty vehicles. It turns out that there's more significant energy benefits obtained using vehicle dynamic solutions than powertrain control alone, and that stands to reason. Hence the requirement for vehicle connectivity. And the vehicle connectivity, as I say, is V2V, V2I, V2Cloud, V2 everything, V2X. Platooning for heavy duty, and I should have put this in parentheses, may not yield as much energy benefit as previously envisioned. That's a result that's shared by a number of other people. And then, of course, connected and automated vehicles sensing power consumption, in addition to the onboard computational loads of these vehicles, are major parasitic loads. And for these prototype or pre-prototype proof of concept vehicles, it's typically very much greater than 1 kilowatt electric, which needs to be reduced to less than something like 500 watts electric continuous power in order not to have a deleterious effect on the range, for example, of BEVs or PHEVs. Now, energy consumption versus trip time trade-off, there's a large behavioral aspect of the driver or the vehicle occupant that's not well understood. What do I mean by that? It turns out that on the average trip, And the average trip clearly is anything between 10 minutes and 5 hours, for example. There's a very strong energy consumption versus trip time trade-off. And most people, if you ask them, are you prepared to trade 10% extra time on your trip for a 10% energy efficiency improvement? They say absolutely no. Under no circumstances are we interested in doing that. Now, if it's a vocational vehicle, perhaps, but for a privately owned, privately operated single ego vehicle, for example, typically the answer is no, under no circumstances. So two things arise. What if you can find an option that's only 1 or 2% longer trip time? Are people more interested in that? And of course, the immediate answer is yes, they'd be more interested. Whether they're interested enough to implement it or to desire it is something else. But there's another issue, which is once vehicles become significantly more automated, does the trip time have the same meaning to the occupants? In other words, if they are distracted doing something completely different, do they know or do they notice that the vehicle has taken 1 or 2% longer than it ordinarily would? So this is a behavioral aspect that we've touched upon in NEXTCAR, but clearly it's not well understood. Look ahead data, which is obtained through connectivity, is extremely valuable for optimizing vehicle longitudinal control over a very wide range of timescales. The longer the time horizon, it turns out, the better in terms of energy efficiency. In other words, up to the full trip length, whether it's minutes or hours. The more information you have, the better in terms of energy efficiency optimization. But even one vehicle ahead, 50-meter or so data is useful. And there's obviously a hierarchy of look-ahead information by timescale, from the machine vision to the V2V, V2I, and eventually V2Cloud. But it's interesting. The energy efficiency improvement asymptotes, but it asymptotes over the full vehicle trip length, and it keeps increasing the usefulness of that data. Energy efficiency gains, and this is point 1, as we call it, are vehicle duty cycle specific, traffic specific, grade specific. I didn't mention that earlier. Technology penetration specific, preview length specific. But 20% is readily obtainable improvement for IC engine vehicles, hybrids, and plug-in hybrids. In fact, the usefulness of look ahead and automation is greatest for plug-in hybrids, a little less for hybrids, a little less for conventional internal combustion engine vehicles, and probably least of all for battery electric vehicles. Of course, because their powertrain control typically is probably as close to, it can be made to be as close to optimal as you can possibly get. But again, 20% is a readily attainable improvement. The current state of the AV industry, as you know, people are marching ahead with L4, L5. This is merely 2 examples of large numbers of vehicle fleets that are working in the area. We're obviously worried as an energy efficiency agency about runaway energy usage associated with L4, L5. And we see from the pandemic, we see a reversion to the primacy of the individually owned, individually operated personal vehicle. In other words, there was a lot of thought about mobility as a service, robo-taxis, if you like, and that they'd be able to be fully BEVs and centrally operated, and somehow this would lead to energy efficiency. We're concerned that the opposite is true, that we're going to see a reversion to the primacy of the individually owned, individually operated vehicle. And then, of course, as levels of automation increase and vehicle safety is not compromised, we're likely to see higher highway speeds, increased VMT, increased vehicle features, and then, of course, longer potential commutes. And the pandemic is throwing a wrench into that particular aspect. If we see more people moving to the suburbs and the exurbs with longer potential commutes made, which can be made more practical due to automation, what does that do to energy consumption? It's not simply us who's concerned about this. This is information from Don McKenzie of the University of Washington and his group showing changes in energy consumption due to vehicle automation that can be entirely undone by travel cost reduction, for example, on the right-hand side. L4, L5, we believe that NEXTCAR technologies will be equally applicable to L4, L5, and there'll be significantly more opportunity for energy efficiency improvements through platooning for a range of vehicles, all the way from light duty, medium, and heavy duty, as well as more opportunities for drive cycle smoothing. How relevant is NEXTCAR today? Well, with the pandemic, as you know, an enormous decrease in average transit usership and average driving, personal owned vehicle driving, but of course it's recovered enormously. And on the right-hand side is data from INRIX that I downloaded this morning that shows in the major metro areas in the United States, it's back up to over 80%, 80% of pre-pandemic passenger vehicle travel levels on average. Okay, so NEXTCAR summary. NEXTCAR has achieved significant results, we believe, for a range of technologies. And the motivation for NEXTCAR is more relevant now than ever before. We need to see the commercialization success as the next critical step. We're interested, we were planning a field demonstration day for the latter half of 2020. Unfortunately, that's going to have to be delayed until 2021. But ARPA-E is always interested in energy efficiency technologies. And I would urge everybody to look out for, we've run an open solicitation every 3 years since 2008. And I would urge you to look out for open 2021. I think that's it. That's all I have to say. Thank you very much.
Thank you very much, and thanks to both. I guess, you know, clap, clap, and I appreciate both of you also staying on time, because I sure know that there are going to be a lot of questions. So with that, I would like to go back, if that's okay, to the question that Greg Collian posted. And I think, Chris, you also touched upon, which is the problem associated with connectivity and sensing and the power consumption. And I think broader perspective of the power consumption, you know, even beyond the boundary of the vehicle, if we are talking about V2I. I think Greg posted this question to Aaron when he was talking. And I think, Chris, you mentioned actually specific numbers. Do you stand by these numbers? Are there better numbers ahead of us from manufacturers that feel that the equipment associated with connectivity will have lower consumption and be more powerful and less consuming?
Yes, I guess there's three things on board, of course. There's the machine vision, and of course, LiDAR, radar, cameras, ultrasonics, all the combination thereof. There's the sensor fusion and computation capability and requirements on board. And then, of course, there's the various modems and things used for vehicle connectivity. At the moment, the sensor fusion and computation requirements are substantial and enormous, and they dwarf connectivity by a significant amount. Nowadays you have vehicles with, we've seen as many as 7 LiDAR and 17 cameras on board the vehicle. There's always the promise that with solid state LiDAR, the total power consumption will drop dramatically. And of course, we believe that too. At what point are these technologies going to emerge? How much level of redundancy do you need on board the vehicle? And of course, these are prototype or proof of concept vehicles that typically have enormous levels of redundancy and extra capability built in. So the magic, the question is always, how much power do these vehicles consume today? We've seen vehicles consuming over 10 kilowatts electric of onboard power today. When you consider that a Nissan Leaf uses 5 kilowatts electric to run across the EPA city cycle on average, that would mean that you would reduce your range for a Nissan Leaf, for example, by 2/3. Clearly, that's completely unacceptable. But in terms of the fact that these are development vehicles, we have to grant them some wiggle room, so to speak. So the billion-dollar question is, what will these power consumption requirements be 5, 10, 15 years down the road? And the answer is no one really knows. It really depends on the level of sophistication of the machine vision that you require, the total number of sensors, the total number of, the total amount of redundancy that you require, and the total amount of onboard computation that's required. Interestingly enough, and I think you might have alluded to that, is that if you can offload not just computation requirements to the cloud, and of course, it's probably not just going to be the cloud, it's going to be the edge, right? The edge of the cloud, because the latencies can be in the single-digit milliseconds as opposed to in the many hundreds of milliseconds of latency for communication with the cloud. If you can communicate with the edge, and if you can have edge computation that can provide information back to the vehicle, well, then you can offload a significant amount of computation off the vehicle. Of course, you have to worry about latency and dropouts of information and miscommunications and cybersecurity and a whole host of technologies. Suffice it to say, we're probably at the very early stages. This is a technology that's in its infancy. And so projecting exactly what the onboard computational and machine vision and sensing, sensor fusion requirements will be 5-10 years down the road, it's very, very difficult to assess. Suffice it to say, it's going to be substantially less than these prototype or proof of concept vehicles.
Thank you, Chris. I can see, actually, not to try to be, okay, I'm going to be picky. I can see Wei Peng over there from M-City. Wei, do you have I know you've been testing and nice background. Okay, can you actually give us an update on this?
Sure. So first of all, we are back in business. We started open on Monday. So companies are already back to test. And from now to end of July, we just have 5 days that have not been booked. So we are very happy to see that companies are still developing these technologies very actively. So I think, like Chris said, most of these vehicles have, prototype. They are just making sure that the vehicles are safe. It's whether they are energy efficient, whether the power is less than 1 kilowatt. That wasn't the point, right? At this moment, eventually they will, but let's look back to the history, right? So when batteries are $1,000 a kilowatt hour, and everybody say, "Oh, that's too much, too expensive, are not acceptable." And when the Wright brothers fly in Kitty Hawk, their airplane doesn't fly very fast, very high, very far. But once we identify the problem, we will solve it. So I think the engineers are very good at identify problem, and eventually they will solve the problem. So if the total power cannot be more than 500 watt, I think they will find the way to do it. So solid state LiDAR is a good solution. Camera doesn't use a lot of power. Computation, I think GPUs, if we need to use GPU, they use a lot of power. But I think that's a problem in comparison to the perception and safety. In comparison, those are smaller problems, and I'm very confident they will be solved.
Okay, thank you, Wei, and congrats for opening and having everybody back in. And I want to circle back in the larger question. You can see from Beth and again from Greg Keolia, and specifically to Aaron about the boundary around the vehicle and the larger system level benefits. Aaron, can I have your attention to that?
Sure. Yeah, that's a challenging question. So, obviously some of these things like the electrification use, we're very interested in sensor use and all that, but that kind of fits into the vehicle itself at least.
Right.
The existing regulations are really tailpipe only regulations. There was a provision in there to look at, we used a net upstream. So for electric vehicles, if enough were sold, but that provision never really came into play. And what that was using upstream estimate minus an estimate of upstream from gasoline, since we don't account for that to kind of offset it. But other than that, and like I said, that was never even used. Those are just tailpipe emissions. And clearly, as we look towards things like electrification, really where that electricity comes from, where it's coming from, and the emission sources that are generating that electricity are far more important, as are some of the battery concerns, I guess.
You mean manufacturing?
Yeah, I mean, yeah. So,
okay.
Yeah, and we are well aware of that. But that then begins to get into some really challenging questions of who's responsible for what emissions. The manufacturers will argue and forever, and I understand why, that the power that their vehicles are using is not something they should be regulated on. And so that is an interesting complication of how do you kind of regulate the power sector versus how do you regulate transportation, and clearly those two sectors are kind of intersecting more and more and more. So I think we're absolutely aware of that. How we actually do it is still, I think, open for discussion, and I think we're very interested and willing to hear about that. And it goes back to the same thing. I mean, like I said, we're used to drawing our box around the car, and so many more things are kind of impinging on that box now with vehicles talking to each other, and infrastructure, and now the power, and talking about, I know Greg was asking about life cycle analysis and these kinds of things. And that's all important and interesting, and I wish I had a better answer of how we're going to do that, and how we'd like to look at it, but it's there.
Okay, I think we're broadening a lot. I think we're broadening a lot of the problem, and I can see also some questions regarding trading and blockchain to Chris.
And I just wanted to add to that, as I said, NEXTCAR is focused on the ego vehicle. Just take eco routing, for example. Any single vehicle can selfishly improve its own energy efficiency at the expense of others. Just so, in other words, you can choose a more energy efficient route through town to go from your origin to your destination, but as soon as other vehicles enter into that roadway space, that then upsets your energy efficiency improvement. In other words, you as the ego vehicle, when you are the only vehicle that has that connectivity, has that capability, has that automation, you are the most efficient one. That's point number one. Point number two is, we know that by drive cycle smoothing, reducing the speed at which you approach an intersection, for example, if the traffic light is red, can improve your energy efficiency, but it simply holds up the traffic behind you, and it causes people to cut in ahead of you, and then upsets your particular trajectory. So, long story short, there are things that a vehicle can do selfishly to optimize its own energy efficiency at the expense of the system. And that's not something that we would like to see, because clearly it's a very, very bad thing. So yes, it's no longer the vehicle, it's now the vehicle in the system, and the system changes in real time, along with traffic and a whole host of other issues along the way. It's a very important, very sort of wider and wider circles of influence of a single vehicle.
So before we move on, I want to ask, so, Aaron said, start taking data now, if we want to, verify. So let's say we do have connectivity, and we do have a vehicle that has, eco A&D, and it has eco driving, and let's say it has more advanced powertrain optimization. Let's say it's a plug-in hybrid and it does blending. Which is, I assume, why it makes the PHEV so high up in your list of benefited categories. So if we are in that domain, can you? So the company, you're saying, can acquire the data, but then on the other hand, we need to have a vehicle that the user cannot turn off the device or the system, right? Is that how do you go about understanding what can be a choice of a customer and how it will be used eventually. And that goes to Aaron. This is the question that goes to Aaron, perhaps. And of course, Chris, you're welcome.
Yeah. So start-stop is a good example. I believe the way we handle it is to be eligible for credits, it has to default on. So I think users can still basically turn the system off, but if it stays off, then I think it becomes ineligible for the credits. So it has to default with each start, I believe, back to being enabled. So yeah, there are ways that you can still have consumer choice, or consumer available to do that. But we have dealt with that in the past. There's different ways with, if you have transmissions with an eco, a sport mode and things. And I again, I don't want to, I'm venturing out of my comfort zone a little bit, but there are ways that we have sort of required manufacturers to do.
Okay, super. And I think that's good. So with that, you see, I think I'm going to switch now to Chris. Chris, there was a question regarding, you qualifying a little bit more, if you can, the hierarchy associated with the PHEVs getting more efficient or efficiency gains.
Yeah, sure. Now, bear in mind a couple of things. One of which is that's on a percentage basis. So in other words, the plug-in hybrids is greater than the hybrid, is greater than the internal combustion engine vehicle, is greater than the BEV. Why is the plug-in hybrids the highest? Because as you know, most plug-in hybrids today simply operate on a charge-depleting, charge-sustaining basis. I'll change my finger, charge-depleting, charge-sustaining. And if you're and it has no knowledge of the trip that it's about to undertake. If you know the trip that you're about to undertake, it turns out. So let me give you for instance. If you're in downtown Detroit and you're going to the Detroit airport, it's city first, then interstate driving later. If you use the electrical energy in the city first, and then the predominantly the internal combustion engine later, that's much more efficient than the reverse. Whereas if you're going from the airport to downtown, the vehicles default into using electric energy first and then engine later. So just by knowing the trip, you can flip that charge depleting, charge sustaining strategy on its head, and you get an immediate 20% is very readily obtained. Of course, it's drive cycle specific, vehicle specific, traffic specific, all of the usual little things with an asterisk that we have to take into account. But it turns out, if you know your trip length, and your trip length is longer than the all-electric range on your plug-in hybrid, any distance longer, and you arrange the charge depletion to be roughly linear over that total trip length, you get a much better result than simply having a charge depleting, charge sustaining strategy. That's why plug-in hybrids are more efficient. HEVs, of course, cannot do the same optimization on a long trip basis, because typically they have less energy, total electrical energy storage capability. And then IC vehicles, of course, you can't say, I'm not going to run the engine now, turn it on in 5 minutes time, because you have no propulsive capability. And then BEVs, as I say, they're relatively straightforward to optimize the propulsion efficiency of the powertrain. You can change things like drive cycle smoothing to reduce foundation brake usage, optimize regenerative braking requirements, and all of those good things. And that's why it's in that cascade, if you like, of plug-in hybrids better than hybrids, hybrids better than conventionals, conventionals better than BEVs. Again, bear in mind, that's on a percentage basis. And of course, the BEV ultimately is the most efficient vehicle of that.
Of the percentage based on its own, on the baseline BEV vehicle.
Yeah.
Okay, very good. I think the other question, let's see, I'm looking here. So there are questions about, again, which powertrain it makes sense, which I think you.
Yeah, so today, if I was a developer, I would use a plug-in hybrid, undoubtedly. But that's today. At some point in the future, you'd be able to have a BEV. There's no reason to, but today a plug-in hybrid will do two things. It'll optimize your range, maximize your range, and optimize your overall energy efficiency and reduce the time required to recharge.
Okay. I'll come back again if there's time. I have a question on this, but I think there is a question on blockchain from Aaron, from Aaron Sargent, that I don't know if you are interested in looking at that, Chris.
Blockchain, at ARPA-E, we have significant interest in blockchain.
Chris, I also sent you a clarification on that question. I don't know if you received it.
Sure.
Do you want me to go ahead and state the better question?
Yeah, Aaron, state it for everybody. Just quickly.
I wasn't sure if we'd get to it. So just to simplify it, I was curious if it's realistic to consider limiting the capability of a single vehicle and basically only use enhanced capability for route prediction and basically increase the connectedness and the data that's passed between vehicles when it's around other vehicles, and how much that increases risk when the vehicle is operating alone relative to the cost reduction to reduce the amount of sensors and processing equipment on board, and also reduce the electrical power consumption.
Yeah, I'll jump into that. As you can well imagine, for fully automated vehicles, let's jump ahead to fully automated vehicles. They're going to have significant robustness with respect to V2X, as well as significant robustness with respect to them onboard machine vision and computation capability. That's then going to limit your capability of offloading that either to the edge or to the cloud or to other vehicles, or however you choose to do it. So, limiting that, your ability to offload the requirements off board your own ego vehicle, means that your own ego vehicle is ultimately going to have that innate capability itself. In other words, you can't simply say, my vehicle will simply coast along with other vehicles and those vehicles will tell it what to do. No, you can't do that, because you can never be fully assured that you're not going to be the only vehicle on the road. So that's going to limit, as I say, the extent to which you can offload these computational requirements off board, which means that you do have to have this redundant capability on board. So I don't see how we're going to get around that. Now, does the redundant capability have to be fully operational all of the time? Well, yes, probably, because you can't have the latency to wake up a microprocessor as your vehicle is approaching a concrete brick wall at 75 miles an hour. So very, very difficult issues, these, very difficult issues. If your vehicle has to have enormous capability at any time, it has to have enormous capability all the time. That is the fundamental issue. Again, related is your vehicle can be the most efficient vehicle on the road, but that might be at the expense of the total cohort of vehicles, and that's to be avoided too. So what's really interesting from a control point of view is that we thought vehicle control would come to an end as a worthy research and development and commercialization avenue. No, it's just beginning. We're at the very early stages. And the problems that we're uncovering now are enormously complex, enormously difficult, and very, very intriguing. That's a plug, Anna.
Yeah, it's a plug because we are running out of time, and I wanted to say that there is a host of questions when we started this program, and also it appears when, let's say, I put myself in the shoes of an OEM that wants to apply for partial credit of cycle credit. And I know that, I will depend not even, let alone automation, but the connectivity And I know that we are very worried about it, but actually within the ARPA-E program, we've developed a lot of tools, and outside, with the DOE and a lot of interest, there are tools that have been developed that show how much you lose, how much of these benefits you can get with full connectivity and high penetration you can lose, but then with tools and controls, robustification, and kind of high risk scenarios that we can tune controllers, you can actually recover quite a bit of that up until quite a bit, but not all. So there is still a lot of work to be done. And I really want to thank Chris for leading this work, and we're very much interested to connect wherever you are, Chris. I think you are close to us now in Michigan, but not exactly Michigan, damn it. And I think it's really good to engage and try to understand what automotive manufacturers are facing, and what are the steps that they have to do to have the customers like the technology and accept it and look for it and pay for it, and also how the manufacturers and the suppliers can actually apply for getting credits that they're helpful for their program. And so, Aaron, thanks a lot for explaining this to us. I frankly, and I think a lot of my colleagues in the controls community outside policy are not familiar with this actually large limitation that manufacturers have. And we wonder, why don't we just do it more? It's 20% fuel efficiency. How come it doesn't happen? So thanks a lot. And with that, I guess if there are other burning questions, we can maybe email them to me, and I will try to go back and forth with Chris and Aaron, or make run a list of questions online that we can send. But I want to be respectful to your timeline, and I want to just maybe turn on your camera and just let's say thanks to Chris and Aaron. So thanks, guys.
Thanks very much.
Thanks for having me.
Yep.
Thank you all. Bye-bye.
We'll do more of that. Thanks. Stay safe, stay well, right? Okay.
You too. Thanks, everybody.
Thank you.
Thanks, Aaron. Good to see you.
Yeah, I appreciate it. Thanks a lot. See you around.
Bye-bye.
Bye. I will recover the recording now. Okay. And